Okay, this is discussion 2.2 on physical and chemical properties and changes. So this is going to tie together a few things that we've been talking about kind of since the beginning here. So first we're going to talk about physical and chemical properties. So what's the difference between a physical and chemical property? So physical properties are things that I can observe without changing the identity of the substance, okay? And chemical properties, when I observe them, change the identity of the substance. So let's think about some examples. I could think of anything I could observe without changing the substance. So I could take the mass of something. I could measure its volume. I could observe its color or its texture. None of those change the identity of the substance, okay? Chemical properties are things like flammability, right? If I set something on fire, I'm definitely going to change the identity of the substance. So this is a not exhaustive list of physical properties, but it's a lot of them. So solubility, the ability to dissolve, is a physical property. When I dissolve something, I'm not actually changing the substance. And think about it, like if you take salt and dissolve it in water, I can evaporate the water and get the salt back, okay? I haven't changed the salt. Color, mass, density, length, volume, the odor, I can smell something without changing it. Temperature, boiling or melting point. When I boil or melt something, I'm not actually changing the substance, I'm just changing its state of matter. If I boil water, it's still H2O. Okay? It's luster or shine, and it's malleability or ductility. We'll define those in a minute. Chemical properties would be flammability, tendency to oxidize, corrosiveness, or reaction with just about anything. So reaction with oxygen, water, acid, etc. Okay? Because when it reacts with those things, it's going to change. So let's practice. Identify which of these would be physical and which of these would be chemical. Pause and then press play when you're ready to go over it. Okay, so color, I can observe that without changing it, so it's physical. If something is flammable, I'm going to change it when I observe that, so that is chemical. Oxidizes easily is chemical. Boiling point is physical, and dissolves in water is also physical. Now, since we're talking about properties, let's go back and talk about the properties of metals and nonmetals. So last time we learned about the areas of the periodic table that have metals and that have nonmetals. So now let's look at some of their properties. So metals have luster or shine. They conduct electricity. They're malleable, which means they can be hammered into a thin sheet, and they're ductile, which means they can be stretched into a wire. Now, conductivity is a physical property because when a metal conducts electricity, it doesn't change substances, right? Otherwise, wires would be, one-time use things, right? Conducting electricity doesn't change the identity of the substance. Nonmetals are dull, so not shiny, brittle, which means if I tried to hammer them into a sheet, they would just break, and insulators rather than conductors. Nonmetals are also much more likely to be a liquid or a gas at room temperature. Metals are almost always solids, except for mercury, which is a liquid at room temperature. So what about metalloids? So metalloids demonstrate some properties of metals and some properties of nonmetals. For example, they might be shiny like a metal, but brittle like a nonmetal. They're usually semiconductors, which means they're partially conductive. And semiconductors have really important applications for computers and technology. Silicon is a very important semiconductor. That's why it's called Silicon Valley, right? Because it's critically important to technology development. All right, so I want you to read these three examples, pause, and see if you can figure out which one is a metal, which one is a nonmetal, and which is a metalloid. And press play when you're ready to go over it. Okay, so first one, substance is dull and brittle. Those are both nonmetal properties, and a gas at room temperature. Also likely to be a nonmetal, so the evidence would suggest that the first substance is a nonmetal. The second says the substance is shiny, which is a metal property, and partially conductive. Solid at room temperature, which could really be either. Brittle when hit with a hammer, so that's a nonmetal property. So it looks like this has a mixture of metal and nonmetal properties, so our best guess would be that the second one is a metalloid. And the last one, it's shiny and conductive, easily hammered into a thin sheet, which is malleability. Those are all metal properties, so the last one is a metal. Now, when we talk about physical properties, there are really two types, intensive and extensive. Intensive properties don't change with amount no matter how much I have. So for example, melting and boiling point, density and color. Now, if I told you that I had a substance that melted at 0 degrees Celsius and boiled at 100 degrees Celsius, chances are you might guess that it's water because you might have heard that before. Water always melts at 0 and always boils at 100 under standard conditions of pressure. So what that means is that I can use that to help me identify a substance. Okay? So that's something that's special about intensive properties. We can use them to help us figure out what we have. The density of water is 1 gram per milliliter. So looking at multiple intensive properties can help me figure out which substance I have. Extensive properties are properties that change with amount. So like mass, energy, length, and volume. If I told you I had 50 grams of a substance, you'd have no clue what it was, right? That could be anything. I could have 50 grams of anything. So extensive properties do not help us identify a substance. Now, a special intensive property that you may not have learned before is specific heat capacity. So specific heat capacity is the amount of energy that's required to raise the temperature of a 1 gram sample of a substance by 1 degree Celsius. So if something has a high specific heat capacity, that means a lot of energy is required to change its temperature. If something has a low specific heat capacity, it's very easy to change its temperature. So I want you to imagine boiling a pot of water on the stove, okay, in like an aluminum pan. If the water had been heating on the stove for about 2 to 3 minutes, what would the pot feel like and what would the water feel like? So assuming that you have a normal stove and not a really, really intense stove, you would expect that the pot would feel pretty warm, right? Metal heats up very quickly, maybe even too hot to touch. The water, on the other hand, assuming you were heating up a decent amount of water, like a full pot of water for pasta or something, the water would just be starting to get warm, okay? Now don't try that at home. I don't want you to stick your hand in water and find out that it's too hot, but the water is going to heat up much more slowly than the pot, okay? And the reason is that metals have a low specific heat capacity, so they change temperature quickly and easily. Substances with a high specific heat capacity, like water, resist changes in temperature. And I mean, just imagine, on the hottest day of the summer in bright sun, if you left out a piece of metal and a cup of water, would you rather stick your hand on the metal in 3 hours or put your hand in the water? I would definitely choose the water. It's going to resist temperature change. You can also think about the beach in June versus October, okay? In June, even though it's hot outside, the water in the ocean is still really cold because it hasn't had time to heat up yet. So even though the sand might be hot and the air might be hot, those change temperature easily, the water takes a long time to heat up. If you go to the beach in September or October, the water is actually warmer, even though it's colder outside because it's been heating all summer long. Okay, so I also want to show you how to do basic calculations with specific heat capacity. We are going to do much, much more with this later on down the line, but I want to introduce it now. So this equation allows us to calculate the heat for a specific substance given the mass of the substance, its specific heat, and the amount of temperature change. So Q equals mc delta T. Q is heat in joules. M is mass in grams, C is specific heat capacity in joules per gram degree Celsius, and delta T is temperature change. When we calculate the temperature change, we do the final temperature minus the initial temperature. And you might already know this, but delta represents change in general, okay? At this point, we are only going to be calculating Q. Down the line, we'll calculate all of those different things and do a lot more with this equation, but for now, we're going to keep it simple. So let's look at an example. The specific heat of water is 4.18 joules per gram degree Celsius. All right, so that's C. How many joules of heat are needed to raise the temperature of a 100-gram sample of water from 20 degrees Celsius to 100 degrees Celsius? Okay. Now, if you want to try this on your own, go ahead and pause for a second and then press play when you're ready to see the answer. I'm going to go over it slowly though, so if you'd rather just see it, that's fine too. Now, I really recommend when you're using an equation that you take the time to write all the variables like I have off to the right here and identify them. Okay, so Q, M, C, and delta T. Q is heat, and that's what we're solving for here. M is the mass, which is 100 grams. C is specific heat, which is 4.18 joules per gram degree Celsius. And delta T is the final minus the initial temperature, so 100 minus 20, so 80 degrees Celsius. So I can now substitute those numbers in for my variables. So Q is equal to 100 grams times 4.18 joules per gram degree Celsius times 80 degrees Celsius, and I would get 33,440 joules. That's a lot of joules, but a joule is a very, very small unit, so that's actually not surprising. Later when we do our energy unit, we'll talk about how many joules are in a single calorie like that you eat, and it's a larger number than you would expect. All right, so the last thing I want to talk about is physical versus chemical changes. Okay, so these are related to the properties. They kind of go together. It helps to understand them together. So physical changes occur when no new substances are created. Okay, now you might have learned back in 8th grade that you can tell a physical change because it's easily reversed, and that's sometimes helpful. But if I tear a piece of paper in half, I mean, I can tape it back together, but I can't really get it back to the way it was before. So I think it's more helpful to ask yourself if a new substance was created or not. Chemical changes occur when one or more new substances is created. So let's look at some examples. Physical changes would be things like tearing, crushing, breaking. None of those things create a new substance. Phase changes, going from solid to liquid to gas, or dissolving. Now, physical changes can be used to separate mixtures, since mixtures are physically combined. Now, chemical changes, there's so many. So when we talk about chemical changes, we tend to talk about indicators that a chemical change has occurred. So some indicators of a chemical change would be a change in color or odor. Now, it's important to note here, you can't just say that color or odor are chemical change indicators. It has to be a change in those. Those are physical properties. So when I see that they've changed, that tells me that I may have a new substance. Production of a gas. Okay, if you see bubbles, that's a good clue. Flames or fire. Okay, a temperature change. Now, I can change the temperature of something without changing its identity. But if I mix two chemicals together and the temperature changes on its own, that is a clue that I might be having a chemical change occurring. But that can occur with both, actually. Production of light, okay, like when we saw the video where they lit magnesium on fire. These are used to separate compounds because compounds are chemically combined. Now, the last thing we're going to talk about is separation techniques. So these are various techniques that we use to separate mixtures. So what you're going to do is watch the Flipgrid video about separation techniques, and then we will talk about these in our lab this week, okay? If you have any questions, just let me know, and good luck.